we will have Gayathri Gururajan, a PhD student from Laboratoire d'Astrophysique de Marseille, and she will talk about high-resolution spectral imaging of CO and C1 and continuum of 3 high redshift lenses that are forming galaxies using ALMA, of course.
So hi, everyone. And firstly, I really thank the organizers for providing me this opportunity to speak. And yes, as you introduced, I'll be talking about the high resolution spectral imaging of 3 dSFGs which are lensed with ALMA. And now, firstly, in context, so the formation and evolution of galaxies is one of the key pieces in order for us to understand the evolution of the universe itself. Now, by studying various galaxies and their properties at different time periods, maybe we will be able to piece together a picture of evolution of galaxies through cosmic time. Massive dSFGs, with like really intense star formation rate can be found at high redshift. They're extremely luminous because of their massive dust reservoir that shines through the intense star formation. But the question, and these galaxies could be the progenitors of the bright central cluster galaxies that we see today. But one question is, how exactly and what really drives this intense star formation? Now, from most widely agreed, there are these 2 major modes of star formation. One is through accretion of cold gas, and the other is a boosted star formation efficiency due to physical processes like mergers. Now, on the plot on the right side, it's the star formation rate plotted against the gas mass. And the black line here, the black solid line here, shows the evolutionary track with redshift of having a higher star formation rate with an increase in gas mass. But there is also another track, that is some galaxies are able to form a boosted, they're able to form more stars with the same amount of gas mass. But such very intense dSFGs, they are usually suspected to have both a combination of a large gas reservoir as well as a high star formation rate. So in order to really understand this question, it will be essential to characterize and understand the composition of the gas reservoir itself, and also identify the morphology and kinematics of such systems. And how exactly are we estimating the gas content here? Traditionally, the CO120 is used as an estimator of the H2 gas. And you also have alternate tracers like the C1 lines, which also trace the extended gas. And both have some advantages and disadvantages over each other. And in order to trace the more dense and warm medium, we can look at the higher JCO lines. And in addition, the dust continuum can also give us a good estimate of the total IR luminosity, which could give us an estimate of the star formation rate. Now, the sample that I will be talking about now is gravitationally lensed, which helps us to get better resolution with a shorter integration time. Now, the 3 galaxies are from the SPT sample, and in all the 3, we observed the C1221, CO726, and the dust continuum emission with ALMA band 5, a resolution of about 0.3 arc seconds and a high signal-to-noise ratio. Now, the first thing you notice when you look at all the 3 spectra is how different they are. All 3 of them are quite asymmetric. And the first thing we wonder is what exactly drives this asymmetry? Like in the case of 0103-45, you can see a very clean unidirectional tail in both the spectral lines. And in the case of 2357-51, you can see a double peak-like structure profile for both the spectral lines. In the case of the continuum emission, all the 3 are gravitationally lensed. So you can see these beautiful ring structures, the lensing arcs and everything. Even though 2357-51 is gravitationally lensed, it still has a very small compact continuum emission. Now, the first thing we do with this is to understand the image plane kinematics. In the case of 0103-45 and 2147-51, the lines are asymmetric, and it will be nice to build a velocity map at every pixel of emission. So what we do is in the 3 sigma region of this source, we extract the spectra at every pixel and correspondingly map the velocity related to it. So over here, both the velocity maps for the sources are built in a similar way. And we can see that the first thing we notice is for both the C1221 and CO726, the velocity maps in both the sources are very similar. This shows the robustness of the method, and they're very consistent with each other. And secondly, we can see a smooth gradient for both the sources that could be suggestive that they're rotating. But in the case of 2357-51, it's interesting to see where exactly the 2 peaks on this spectra arise from. So what we did is at every pixel, we decompose the spectra of each line into 2 Gaussians, one representing the lower velocities, that is the blue component, and the other representing the red component. And the resulting velocity map is shown here. So the red component for both the lines has a smooth gradient, and in the case of the blue component has a smooth gradient, and in case of the red component, it's more distorted. And also here, what we do is to overplot the continuum contours, and we can see how the red component is aligning better with the continuum compared to the blue component. Maybe this could indicate that these 2 components are intrinsically different, and maybe it's a merging system. To go further and study our properties in source plane, we attempt at a lens modeling. We use the visibility-based lens modeling code VisiLens from Justin Spilker's 2016 paper. And the modeling itself is a bit challenging with the resolution that we have. So in the case of 0103-45, the best model that we could get required the source profile to have a 2-component system, one more extended and one a very compact component. For the other 2 sources, a single component system was could well model the entire source. And because we have significant SNR, in order to model the line emission, what we do is to divide the spectra into velocity bins of roughly 500 km per second and model each of the bins. Also, since our continuum is at a better resolution and better SNR, what we do is to model the continuum, obtain the best fit parameters, and use them as a starting value for our line models. And here is the reconstructed source plane velocity maps. So basically what these maps are, they're the positions corresponding to the source plane model at every velocity bin. So it's basically the same as what we saw earlier, but in source plane. And if you see in the case of 0103-45 and 2147-50, you can see a smooth gradient, and these sources are most likely rotating disks. In the case of 235751, however, you don't really see a single gradient or anything like that. And when you compare it with the PV diagram constructed in the image plane, we can see like 2 blobs separated by about 400 km per second. And maybe this is actually a merging system. The other thing what we probe is to see how exactly differential magnification plays a role in these sources. Now, in the case of the effective magnification of the continuum and line, the variation is less than 24%. So the flux itself, it's not highly affected by the differential magnification. However, the plots on the right show the variation of magnification along with each velocity bin. And the dashed line here represents the observed spectra. It's really surprising to see how in the case of 0103-45 and 2147-50, the observed spectra seems to be the asymmetry seems to be dominated by a magnification effect. Like if we see the magnification plot, it's almost coinciding with the observed spectra. So maybe this asymmetry is completely arising due to a magnification effect. However, in the case of 2357-51, this double peak-like structure seems to be more intrinsic rather than driven by magnification. Now, because we don't really have a significant differential magnification, we continue to do the resolved line and continuum analysis in the source plane itself. The image plane itself. So the first thing what we did was to compute the luminosity ratio of both the lines and the C1221 compared to the IR luminosity, and compared our sample with the sample in literature. For example, Valentino 2020 had a very big compilation of SMGs, main sequence at redshift 1, and local galaxies. So we compared our sample to see how they varied. And we also use the radiation field and the density tracks, isocontours modeled with the PDR modeling of Kaufman 99. And we can see that the C1221 to CO7-6 ratio is, the lines are parallel to the isocontours of the density. So this could be used as a good proxy to the density. Similarly, the C1221 to LIR ratio is a good proxy to the radiation field. We also try to understand how these ratios vary across the ISM of our source. So for this, we calculated these ratios across the entire source and at every pixel, which are represented by the small pixels on the 3 plots. And we can see how the ISM of the source is quite heterogeneous. It varies a lot in terms of radiation field, and for 2147-50, even in terms of density across the source. And to conclude, all our sources are compatible with the SMGs and the main sequence at redshift 1 in terms of density as well as radiation field. So from all our data, we can also compute, we can compute the star formation rate intrinsically, because we can correct for our magnification. And we can also estimate the gas mass of our sample from the ancillary CO3-2 data. And for one of our source, we even have a CO1-0. So the other thing what we can do is to compute the dynamical mass of the system, because we have an estimate of our source size as well as the axis ratio, so we can correct for the rotational velocity better. And from this, we can compare how the dynamical mass and the gas mass is faring. So using different alpha COs, we can see that the dynamical mass seems to be more agreeable with a lower alpha CO of roughly 0.8, whereas a higher alpha CO of 3.4, it's in tension with the dynamical mass. And these lower alpha COs give us a very short depletion time scale, less than 100 mega years for all our sources. In order to conclude, so first we computed the star formation rate, surface star formation density, dynamical mass, gas mass, and depletion time scale for our sample. And using the different alpha COs and conversion factors of CO, we can compute the gas mass. And the gas mass seemed to be more in agreement with the dynamical mass for a lower alpha CO. So from this, we can conclude that our sample is morphokinetically diverse, from rotating starbursting disks to merging systems. Extending this analysis to a larger sample could help us identify dominant morphologies at this redshift. Thank you.
Thank you very much. Very interesting work on lensed modeling.
Thank you.
I have some curiosity, if there are no questions. Okay. So are you talking about visibility-based lensed modeling? I am not in the field, sorry, my ignorance. There are also image-based modeling, or?
Image-based, I'm not sure, but there are other modeling techniques like pixelated reconstructions.
Okay.
So but image, generally you do it on visibilities to avoid a lot of these correlation errors, and it reduces the errors and assumptions significantly.
Okay. And if you came back to the result slide,
yeah,
I'm just wondering the largest error bar will come from and how to reduce them.
I think I'm not sure with the other sample, and here basically the 3 squares are what we do, but I think with depletion time scale, one of the main error will be with the gas mass and the star formation. So I think I'm not sure exactly how we can reduce these, maybe more accurate, probably with star formation rate. I think with I'm not sure actually, to be honest. Yeah.
And you said that are you planning also to enlarge the sample, right?
Yeah.
Do you have already some candidates?
Actually, yes. So we have around 30 candidates selected and we'll be submitting a proposal in the upcoming cycle.
Okay, so good luck.
Thank you. Thank you.
There is a question.
Okay.
Do you think there are more molecular species that can be detected in those lenses?
I'm sorry, I didn't understand.
Do you think there are more molecules, other molecules that you can detect?
Yeah, actually, there are a lot of ancillary data for these sources. You know, you have the CO3 to 2, CO4 to 3, but other molecules, I think sometimes H2O and HCN can be detected as well. But
So,
it depends on the redshift, actually. I have to check.
Yeah, actually, can you remind me, I probably missed it at the beginning, which is the redshift for these sources and which is the redshift of lens that you estimate?
I don't know the lenses redshift on top of my head, but it's around redshift 2 point something for one of the source. I'm not sure of the other three, but for all the three sources, the first 0103 minus 45 is about 3.08, and 2147 minus 50 is 3.76, and 2357 minus 51 is 3.09. So
Okay.
roughly 3 to 4.
Thanks. No other questions from the chat.
Okay, thank you.
I think we can stop here. Thank you again for your talk.